My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I would like to welcome you all to our International Physics webinar. Good evening to all here in Bangladesh, and a very good afternoon to all those who are watching this program live from UK. So hope you are well and safe from Corona pandemic. Today it's our 107th International Physics webinar. So all we know that we are staying in a Corona pandemic situation. We cannot continue our normal academic program inside the campus. We have to start our online program. So I think you have come to know that our Department of Physics, Pabna University of Science and Technology, has started its online program, including the online international physics webinar. And we have successfully completed our 106th international physics webinar. So the main aim of our program is to motivate and encourage our students in this Corona pandemic situation. We are trying to adjust with this new normal situation. Today is very important day for our department. Today I'd like to welcome you all to a joint session between the Department of Physics, Pabna University of Science and Technology, and the Applied Mathematics and Theoretical Physics Royal Society University Research Fellow and University of Southampton, UK in physics. So we have with us here today Dr. Angie O. Bannon, lecturer, Applied Mathematics and Theoretical Physics Royal Society University Research Fellow at the STAG Research Center of the University of Southampton, University Road, UK, connecting with us from UK. So he has already connected with us. So I'd like to welcome our speaker. So good evening, sir, and very good afternoon to your part, and welcome to our International Physics webinar. And thanks for accepting our invitation, sir.
Oh, well, thanks for inviting me. Should I go ahead and start?
Yeah, of course. And we'd like to say thanks on the behalf of the Department of Physics for accepting our invitation.
Sure. So can you see my slides?
Yes, sir, we can see.
Okay. Yeah, well, thanks for inviting me. I'm honored to be here speaking to you today. And I'm going to discuss a question you've probably never thought of before. Is our universe a hologram? Let's see, hold on. Okay, so what I'm going to talk about is my research. And if I had to summarize my research in a single sentence, it would be this. I use a tool from string theory called holography to study strongly interacting systems. And I assume most of you may not know what these three things are: string theory, holography, and strongly interacting systems. And so what I'm going to do in my talk is I'm going to go through each of these things one at a time and tell you what they are, at least a little bit something about what they are, why you should care about them, and what they have to do with each other. And I'm going to start with string theory. So in order to explain string theory, I'm going to discuss the two major achievements of 20th century physics, namely quantum mechanics and Einstein's theory of relativity, the general theory. But I'm going to start with quantum mechanics. And to discuss quantum mechanics, I'll start with quantum mechanics. As most of you probably know, very broadly speaking, quantum mechanics describes physics of the very small. So again, generally speaking, things on the size of an atom or atoms and smaller. So how small are we talking about? Well, for example, if you take a normal everyday object, like say an iron skillet, pictured on the left, which is, let's say, roughly 30 centimeters across, we know that if you look closely enough at that, it's made of iron atoms. I've pictured an iron atom on the right. How big is an iron atom? Well, roughly speaking, about 10 to the minus 8 centimeters. So those are the kind of scales we're talking about. And as this, I should say, this is an artist's depiction of an iron atom. This is not data or anything. But as the picture indicates, the atom is not a fundamental particle. It is made of smaller particles. Oops. And as the picture shows, what's inside the atom? Well, at the center you have the nucleus, and then orbiting around the nucleus are the electrons. Now, as far as we know, the electrons are fundamental particles. So at this point in history, we do not have any evidence, experimental evidence, that they're made of anything smaller. However, the nucleus, we know, is not a fundamental particle. It is made of smaller things. First of all, how big is the nucleus? Well, if the atom is 10 to the minus 8 centimeters, then the nucleus is about 10 to the minus 12 centimeters across. So that's about, what is that? About 1, 2, 3, 4, 1/10,000th the size of the atom. And as I've depicted here, again, this is an artist's depiction. The nucleus is not a fundamental particle. It's made of smaller things. It's made of two kinds of particles called protons and neutrons. How big is a proton or a neutron? Well, it's about 10 to the minus 13 centimeters across. And it doesn't end there, because we know that protons and neutrons are also not fundamental particles. They are made of even smaller things called quarks. And as I've shown here, a single proton or a single neutron is made up of 3 quarks. And how big is a quark? Well, here we get to the limits of the experiments. I can't tell you exactly how big a quark is, because we're reaching the bounds of the experiments, but I do know that it has to be smaller than a proton or neutron, so it needs to be smaller than 10 to the minus 13 centimeters. And that's the current state of the art. So at this moment in history, as far as we know, the electrons and the quarks are fundamental particles, and quantum mechanics governs their interactions with each other. I should say, the theory that describes the electrons and the quarks and their interactions with each other is called the Standard Model of Particle Physics. It was developed by the generation after World War II. I've pictured some of the people here. These are people who won, some of the people who won Nobel Prizes for their work on the Standard Model. They, of course, they're mostly white men from Europe and North America, although nowadays we're trying to change that. And of course, they were building on the work that was done before World War II. In the 1920s and 1930s, that's when quantum mechanics was developed. And I've pictured some of the people who developed that theory here. Again, these are some of the Nobel Prize winners who worked on quantum mechanics. And in particular, I wanted to focus on one of these people, namely Heisenberg. Nowadays, the name Heisenberg is famous because of the TV show Breaking Bad, which maybe some of you have heard of. To be honest, I've never seen it. However, I have a personal connection to Heisenberg, sort of, because my first physics job, the first time I ever got paid to do physics, was at the Werner Heisenberg Institute in Munich, Germany. And there's a photograph of the institute there on the left. And on the first day of the job, I showed up and they didn't have an office for me yet. So they temporarily put me in Heisenberg's office. It was the office that he actually had when he was at the institute. And they had his original desk and his original chair. And then on the walls, they had portraits and photographs of Heisenberg all over the walls, actually. And so for me, in my first day as a real physicist getting paid to do physics, it was very intimidating to be sitting at Heisenberg's desk with lots of pictures of Heisenberg staring down at me. But eventually I got my own office, and it turned out to be a really fun job. Anyway, I focus on Heisenberg because, of course, one of the fundamental principles of quantum mechanics is the Heisenberg uncertainty principle, which a lot of you probably know. The simple statement of it is that the more precisely a particle is positioned is determined, the less precisely its momentum can be determined, and vice versa. So if you measure the position to more and more decimal places, you will only be able to measure the momentum to fewer and fewer decimal places, and vice versa. So in other words, there will always be some uncertainty in one or the other, and usually it's both, because you can never measure either of them with perfect precision. And because of the uncertainty principle, quantum mechanics, of course, is probabilistic. So what does that mean? Well, as a physicist, and specifically as a theoretical physicist, what I want to do is take some equations, do some calculation, and get a number that I can compare to the experiments. But in a theory that's probabilistic, you don't just calculate one number. As I've tried to indicate here, what you actually calculate is all the possible outcomes of the experiments. And associated with each of those is some probability, the likelihood of finding that particular outcome. So for example, maybe outcome number 1 has a 20% probability, outcome number 2 has a 15% probability, and so on. And the crucial thing, this was a big conceptual change. Of course, historically at the time, this was a big conceptual change. This was not something that physicists were used to doing. And it caused a lot of anxiety and a lot of debates and so on. However, at the end of the day, people accepted it. And that's largely because you don't really lose any predictability. I mean, the theory is still, you can still make predictions. It's just the nature of the prediction changes a little bit. So the prediction is not just, that if you do the experiment, you get this one number. And instead, the prediction is, well, if you do the experiment 100 times, well, 20 times you'll get outcome number 1, 15 times you'll get outcome number 2, and so on. But there is uncertainty, and there are probabilities involved in quantum mechanics. And as I said, it was a radical change. So you have to, when you get down to these scales, when you're in a realm where quantum mechanics applies, simple pictures like this one no longer apply. So this would be, before quantum mechanics, this would be the simple picture of the hydrogen atom with the proton being the nucleus at the center, surrounded or being orbited by an electron around the outside. But once you get to quantum mechanics, you realize, well, this isn't correct anymore. In the world of quantum mechanics, the hydrogen atom actually looks like this. And so what I've drawn here, well, you're physicists, and in fact, you've probably done this problem. This is now a textbook problem. This is solving the Schrodinger equation with a Coulomb potential and calculating the ground state. And what I've plotted here is actually the probability density of the ground state. And what you see is that it's a cloud. The density of this cloud tells you how likely it is to find the electron at that location. And so what you observe is, in principle, the electron can be anywhere, but it's just much more likely to be, say, at the center than somewhere off far away. But my real point is that you have this uncertainty, you deal with probabilities, and that was a big change. All that being said, as I tried to emphasize, that doesn't mean that the theory is any less predictive. And in particular, the standard model of particle physics, which describes the interactions of these microscopic particles, the electrons and the quarks, and which is a fully quantum mechanical theory, is one of, if not the most successful theory in the history of physics, because it can explain and predict an enormous number of very different phenomena. And so I'll try to give you a sampling of some of those. In particular, it can describe essentially all electric and magnetic phenomena, such as static electricity and lightning, and electrical currents, and magnetism, like in your refrigerator magnet. It also essentially describes atomic physics because it describes very precisely the structure of electronic energy levels in atoms. And so ultimately, it explains the structure of the periodic table, and therefore all of chemistry. And it doesn't end there. It can also describe radioactivity and nuclear physics, including both the fission reactions that happen in nuclear reactors that are used in power plants, as well as the fusion reactions that happen in nuclear weapons. And it can also describe the nuclear reactions that happen in the sun, which of course is where the sun's light and heat comes from. So we have this one theory, the standard model of particle physics, which is fully quantum mechanical and which can describe all of those phenomena to great accuracy. And as I said, it's one of the most successful theories for that reason. However, it's incomplete because it doesn't describe gravity. So although it can describe the nuclear reactions that happen in the sun, it can't describe, and it doesn't describe, the gravitational interaction that actually holds the sun together. We have a different theory for that, and that's what brings me to the other major achievement of 20th century physics, namely Einstein's theory of relativity. Because Einstein's theory, and I'm thinking here of the general theory of relativity, that's a theory of gravity. So I'll very briefly go through that and just give you a sketch of how that works without using any equations. So first of all, I'll just mention the history. The general theory of relativity was developed in the 1910s and 20s, overlapping a little bit with quantum mechanics. And it was developed, at least in the beginning, mainly by Einstein. He was the one who had the main conceptual breakthroughs, although of course lots of other people started working on it soon thereafter. And okay, again, I'm going to go through this without any equations. I'm going to try to just give you the idea. Einstein's main conceptual breakthrough was to think of space and time as malleable. So you should not think of points of space and time as some kind of rigid structure, like a rigid lattice or something. Instead, you should think of it as malleable. So you should think of it as something like Play-Doh or silly putty or bread dough. So it can bend and warp and deform. And also similar to bread rising in the oven, it can expand. And in fact, we think that's what's happening. We think the universe is expanding today. And moreover, the amount of warping or bending or deforming is related to the amount of matter and energy. So in particular, if you have a very heavy object, it will bend space and time a whole lot. And then if you have lighter objects, they will bend space and time much less. And the amount of bending is what we experience as the gravitational force, or more precisely, the gravitational interaction. So for example, if you have a very heavy object, like say a star, which this is again an artist's depiction here, it will warp space and time a whole lot. And then if another object, smaller object comes along, well, the smaller object will technically deform the space as well, but not as much. I'm assuming it's much lighter so that you can ignore any warping that comes from the small object. What will happen is the small object will come in, and because of the warping, its trajectory will be changed. And that change in the trajectory due to the warping of space and time is what we would observe as the orbit of that object around the star. That's pretty much all I'm going to say about general relativity without going into any more details. However, what I want to emphasize is that Einstein's theory has also been very successful. But in general, Einstein's theory, and again, this is broadly speaking, it describes things that are very big, planets and stars and things like that, that are very massive and that deform space and time a lot. And how big are we talking about? Well, for example, Einstein's theory can very accurately describe the orbits of satellites around the Earth. Again, this is an artist's depiction. How big are those orbits? Well, they're broadly speaking around 30,000 kilometers. Einstein's theory can also very accurately describe the orbits of planets around the sun and also the orbits of planets around other stars. How big are those? Well, again, broadly speaking, that's around 10 to the 9 kilometers. And I can keep going. So for example, Einstein's theory can very accurately describe the motion of stars in the galaxy or in a galaxy. And I'm including dark matter here. You can include that in Einstein's theory. We don't know what it's made of, but you can include it in Einstein's theory. It's equation of state anyway. How big is a typical galaxy? Well, it's something like 10 to the 18 kilometers across. And I can keep going to even larger scales, to some of the largest scales that we know about, namely the distances between galaxies and even larger. So Einstein's theory can very accurately describe the interactions of galaxies with each other. What's the typical distance between galaxies? Well, around 10 to the 19 to 10 to the 23 kilometers. And in fact, you can go all the way up to the size of the observable universe, which is somewhere around 10 to the 23 kilometers. So on these types of scales, Einstein's theory is extremely good at predicting the motion of objects. However, Einstein's theory is also incomplete. In particular, it is not quantum mechanical. And what I want to convince you of is that that's a problem because the real world has both quantum mechanics and gravity happening at the same time. So those electrons and quarks of the standard model do experience a gravitational interaction. And in fact, the planets and stars and galaxies are fundamentally made of quarks and electrons, as well as things like dark matter. And so we know that any gravitational interaction that between stars and planets or within a galaxy has to fundamentally be coming from the quarks and electrons. But there's a question of, well, okay, so we have these two major achievements, quantum mechanics and Einstein's theory, and they've both been very successful in these different realms of either the very small or the very big. So how can that be? I mean, if both quantum mechanics, the universe we actually live in has both quantum mechanics and gravity, and they're happening at the same time, well, how can each one be so successful? And the answer is, well, usually you can ignore one or the other. So yes, we know that electrons and quarks must have some gravitational interaction. But when you compare that to, say, the electromagnetic interaction, it's really, really tiny. The gravitational attraction is so small, in fact, that you can essentially ignore it for practically everything you do at the scale of an atom or at the scale of a nucleus. However, I still would argue, and I still want to argue, that you have a problem that neither theory is complete because there are cases where you can't ignore one or the other. There are cases where you really need to have both at the same time. And the two main examples of that are black holes and the Big Bang. So if you don't know what these are, I'll just briefly say that a black hole is created if you cram so much matter into such a small space that the matter actually collapses into itself, and the gravity becomes so strong that even light cannot escape, and therefore nothing else can escape. This is why it's called a black hole. And I've pictured here on the right, this is a famous image you may have seen of a recent observation of a black hole. So you're not actually, in this picture, you're not actually looking at the black hole because the black hole itself, of course, doesn't emit any light, but there's stuff around the black hole which does emit light, and that's what this image was. But anyway, let's see, the other example is the Big Bang, and this one is relatively easy to explain. So as I mentioned before, we believe now, or we know now, that the universe is expanding, but that means if you run the clock backwards, if you go backwards in time, eventually everything in the universe started at a single point. So you're taking all the matter and energy in the universe and you're cramming it into a single point. And so in both of those cases, you're getting very strong gravity, you're getting a large amount of matter and energy, but in a very small space. So you have a lot of matter and energy, so gravity is important, but it's in a very small space, so quantum mechanics is also important. So these are cases, so because, for that reason, these are cases where you have to deal with quantum mechanics and gravity at the same time. So you can't ignore one or the other. And so these are cases that cannot be explained or described very well by either the Standard Model or Einstein's theory alone. Both of them, either one of them actually will break down in these cases. And so the two major achievements of 20th century physics, namely quantum mechanics and Einstein's relativity, give rise to the major problem of 21st century physics, namely how to combine the two. So how do we write down a theory that has both quantum mechanics and gravity in it? This is called the problem of quantum gravity, or the theory of everything. That's what people are trying to find. I should say everything means everything in physics. It doesn't mean literally everything like economics and art history and stuff. It means can we write down a single theory that describes all of the phenomena, physical phenomena we see, including both gravity and quantum mechanics. And in general, well, I should say, the most important thing to say, this is an unsolved problem. At this moment in history, we do not know the theory of quantum gravity or the theory of everything that describes our universe. We believe one exists, but we don't know what it is. It's a very difficult problem. For about 100 years now, a lot of very smart people, people much smarter than me, have been working on it. And so far, they've always failed. Every time you try to combine these two theories, something goes wrong, usually very badly wrong. For example, quantities that are supposed to be finite diverge, or they're zero. Things just don't make sense. It's an extremely difficult problem that remains unsolved. However, this is where string theory comes in. Because string theory at this moment in time, it's our best guess for the theory of quantum gravity, or the theory of everything. And I should mention that the difficulty, the fact that this problem is so difficult is just telling you that you need it's going to require a big conceptual change. It's not something where you just work harder with the equations we have and you'll eventually solve it. You're going to need some new ideas, some new concepts, and a new starting point. And that's what string theory gives you. So I'm going to very briefly go through and try to explain a little bit about what string theory is in relatively simple terms. First of all, a little bit of history. So string theory was developed by the generation after the Standard Model, so mostly in the 70s and 80s and going into the 90s. Nobody's won a Nobel Prize for string theory. Nevertheless, I've pictured some of the main people involved here. By the way, it's still mostly white men from Europe and North America. But I wanted to point out one person in particular, which was Michael Green, who's pictured there on the left, because in my second physics job, that was at the University of Cambridge, and he was my boss. And that was also very intimidating to show up on my first day of work for my second job. And my boss was now one of the founding fathers of string theory, Michael Green. But he turned out to be a really nice guy, and it was a fun job. So everything worked out in the end. Anyway, okay, so what is string theory? Okay, so string theory begins with a question, a what-if question. Namely, what if the electrons and the quarks are not fundamental particles? What if they are made of something smaller? So of course, we're now leaving the realm of experiments. We're going beyond the experimental limits because as I mentioned before, as far as we know, the electrons and quarks are fundamental. At least we have no experimental evidence that they are made of anything smaller, but string theory begins with this question asking what if they are? And in particular, of course, string theory proposes that, well, these particles are made of little strings, which I've tried to draw here on the right. This is an artist's depiction of a string in string theory. And of course, when you say string theory, or when you mention a string, the very first question people always ask is, well, what is it made of? Because when you say string, people usually think of twine or yarn or something like that. And of course, that's not correct. Because in string theory, the strings are supposed to be the fundamental objects. They're not made of anything small. So if you ask what is the string of string theory made of, well, I'll give you the answer that my PhD supervisor gave to me. They're not made of anything smaller. They're just pure energy, little strings of pure energy. And if you want some mental image of what that might look like, this is an artist's depiction of a highly excited string that's moving around somehow, and it's just made of pure energy. Why do we call them strings, though? Okay. If they're just pure energy, why do we call them strings? Well, it's because of the way they move. And in fact, the way they move is very similar to the string on a violin or a guitar or in a piano. Namely, they can vibrate. They can vibrate with different frequencies. And the higher the frequency, the higher the energy. And in fact, the difference between an electron and a quark is precisely the frequency at which the string vibrates. So the quark and the electron are supposed to be made of the same type of string, but just vibrating at different frequencies, as I've tried to draw in this picture. So the quark, for example, would be a string vibrating with a higher frequency. Now, from that simple starting point, I'm going to skip a bunch of steps because there's a bunch of math you have to do. But what it turns out, in the end, and it's quite remarkable, and this is the technical part, which is why I'm going to skip it, but it turns out that string theory actually is a theory of quantum gravity. So you can show that, in fact, string theory is fully quantum mechanical, includes quantum mechanics, and in fact, it can describe the electrons and the quarks. And in principle, at least, it can describe the standard model of particle physics. But it can also describe Einstein's theory of relativity. You can actually get both of those theories out of string theory. And so this is why it's a theory of quantum gravity. It's the first time when people have been able to combine these two things without getting answers that are obviously wrong or obviously trivial. So it doesn't have any of the sicknesses of other attempts to unify quantum mechanics with Einstein's relativity. That's not the end of the story, of course, because it's perfectly fine, theoretically, at least the equations are okay, but that doesn't mean it's right, because in physics, a theory is only right if it agrees with experiments. So the crucial test is, okay, can we test string theory experimentally? And as you've probably guessed or anticipated, the answer is no. There's a number of reasons this is true. I'll give you one of them, probably the most important one. You can ask a very simple question of, how big do the strings of string theory have to be in order for string theory to be a theory of quantum gravity? And again, there's some math, that goes into this. I'll skip the details, and I'll just tell you the answer. The answer turns out to be about 10 to the minus 33 centimeters. So that's 20 orders of magnitude smaller than the current experimental limits. And of course, this is why string theory has never been tested experimentally, and it's also very difficult to imagine how you ever could, how you could ever design an experiment that could reach these very short distances. However, you should never say never. People are very clever, and they're always trying to think of ways to test string theory. For example, maybe indirectly, or in lots of different ways. And there's lots of proposals out there, but it's a very difficult problem to try and test string theory. So it's a perfectly wonderful, theoretical solution or example of a theory of quantum gravity. It's the only one, or at least the leading candidate we have, but it's very difficult to test. And that could be the end of the story. Okay, well, so that was my very brief summary of string theory, of what it is and why you should care about it. And that could have been the end of the story of just, throw up your hands and say, well, it's just too difficult, we can't do anything, except for holography. Because holography gives you a very different perspective of what string theory is and what it's good for. So what I'm going to do now is I'm going to very briefly go through and try and explain some of the basic principles of holography. So again, starting with a little history, holography was developed starting in the 1990s up until the present day, so it's still a very active field of research. The main people who get credit for the idea of holography are pictured here: Susskind, Maldacena, and 't Hooft. 't Hooft is Dutch, by the way. And actually, 't Hooft does have a Nobel Prize. He didn't win it for holography, though. He actually won it for his work on the standard model of particle physics. But I want to focus on Juan Maldacena. So that's this guy. He's Argentinian, although now he lives in the US. And back in 1997, he was working on string theory, but with an additional ingredient. He was working on a special case. In particular, he was studying string theory on a space with a boundary. And so this is my very crude picture. So I have some strings. There's some string theory with some strings moving around and interacting with each other in some space that has a boundary. And so the blue rectangle is supposed to represent the boundary of the space. So that's like a wall where the space ends, and the space does not continue beyond that. And actually, the way I've drawn it, the blue rectangle is supposed to be sort of in the background, and the black lines are supposed to be coming towards you. I don't know. Some people have told me the picture is confusing, but anyway, you'll see later in the pictures coming up what I have in mind. So anyway, Maldacena was studying this string theory on a space with the boundary, and he made a remarkable discovery. He discovered that the equations describing the interactions of the strings were actually, they were equivalent to a different set of equations. A different set of equations that seemed to describe a very different system. Namely, he discovered that the equations describing the strings were actually equivalent to equations describing quantum mechanical particles that had no gravity. So in fact, a system very similar to the standard model of particle physics, where you have some quantum mechanical particles and they're interacting, but there's no gravity. And moreover, they're stuck at the boundary. And again, just to repeat the main points, he discovered that these two things are equivalent. So what he found was there's some set of equations that describe the strings moving on the space with the boundary. There's a different set of equations that describe some quantum mechanical particles with no gravity, and they're stuck at the boundary. And his discovery was that, although these two sets of equations look very different, they seem to be radically different. In fact, secretly, they're the same, if you know how to translate from one to the other. So I'll try to give you some very crude idea of how this works, okay? Because what this is saying is that basically anything that the strings do, the particles will know about, and anything the particles do, the strings will know about. So let me give you an example. So suppose I have a string that's just moving along in some direction with some momentum. And by the way, it's quantum mechanical, so yes, it will be subject to Heisenberg uncertainty, although that won't be very important for what I'm talking about. Okay, so the string's moving along, and the claim is that, the particles living at the boundary will somehow know about this. So how do they know about it? Well, what will happen is you'll see a bunch of them lumped together and moving along in the same direction as the string with the same momentum. So the string is represented by the particles as this lump of particles moving along in the same direction. But of course, the strings can move in one extra dimension, right? Because they can move away from the boundary or towards the boundary. So how do the particles know about that? Well, if the string moves directly away from the boundary, what will happen is this lump of particles will actually start to spread out. And of course, if the string moves towards the boundary, it'll get more and more dense. And so in this fashion, the strings can actually encode anything the particles at the boundary can encode anything that the strings are doing. Any motion or interaction of the strings can actually be encoded by the motion and interaction of the particles at the boundary. So it really is, I hope this helps with the intuition, but intuitively, it really is like you're shining a light on the string and it's casting a shadow on the boundary where that shadow is made out of these particles. So that anything the string does, the particles will correspondingly do something. And this is called holography. So why is it called holography? Well, first of all, there are holograms in the real world. And in fact, a lot of you probably have a credit card. Every credit card has a hologram of a flying bird on it. And that's just because holograms are very difficult to counterfeit. It's very hard to make a hologram, especially one that's small. It's very hard to copy a hologram also. So that's a security. So for a credit card, that's a security feature. But anyway, in the real world, a hologram is a two-dimensional flat image, but it contains enough information to reconstruct a three-dimensional object. So this hologram of the bird actually has enough information to reconstruct not only the width and height of the bird, but also the length, the information in the third dimension. And the idea is that's what's happening here with the string theory, that somehow these particles living at the boundary actually contain enough information to reconstruct the whole string theory. So those equations describing the particles at the boundary actually contain enough information to reconstruct the equations describing the strings. And so in that sense, the particles at the boundary really are the hologram of the string theory. And that's why it's called holography, in analogy with real holograms. And in fact, Susskind and 't Hooft actually elevated this to a principle called the holographic principle of saying, they proposed at least, that this should be a property of any theory of quantum gravity. It doesn't have to be a string theory. But anyway, they have proposed that in any theory of quantum gravity, if you take any region of space, well, first of all, if you have a boundary, then whatever equations describe your quantum gravity theory, there will be some other set of equations describing particles at the boundary that will contain all the information of your quantum gravity theory. And they even went farther and said, well, you can just take any chunk of space that has quantum gravity in it, and at the boundary of that space, you'll have some quantum mechanical particles that contain all the information inside. I should say at this point, this is a proposal or a conjecture. It's very difficult to prove, and it's also not terribly helpful because it doesn't tell you very much about the particles. It just is a proposal that they exist, that there should be some lower dimensional description of quantum gravity, but it doesn't tell you what it is or how to find it or anything like that. I should say, though, that if it is true, it's a profound statement, because what it's telling you, so going back to this picture, what it's telling you is that actually your string theory or your quantum gravity theory is actually much simpler than you think. Secretly, you can translate it into some much simpler theory of just quantum mechanical particles interacting without gravity. And vice versa, if you start with the quantum mechanical particles, it's telling you that somehow they secretly know about quantum gravity, going the other way. And in fact, it raises lots of deep and profound questions like, okay, how does any of this work? What are you talking about? And in particular, what is the dictionary? So I've said, several times now that, okay, you have these two sets of equations and they're equivalents. If you know how to translate between them, what is the actual dictionary? How does that actually work? That's an open question. It's a topic of active research today, so I can't answer it completely for you. There was a lot known about it, at least in some cases. It also raises questions about our own universe. Like, for example, so in our universe, we believe there is some quantum theory of gravity. We don't know what it is yet, but we believe it exists. Does that mean that, out at the edge of the universe, there's some boundary with some quantum mechanical particles that are the hologram for our universe, for everything happening in our universe? Or, another question you can ask is, well, the standard model is some quantum mechanical theory of particles, interacting without gravity. Is that the hologram of some quantum gravity theory in some higher dimension? And then a really difficult question is, can we test the holographic principle experimentally? I don't even really have a lot of great ideas for how to do that. And indeed, I'm not going to answer any of these questions. As I mentioned, these are all topics of active research that people have been working on for the last 20 or 25 years. So I can't answer all of them. But, well, okay, so that's my very brief review of holography and what it is. Hope it wasn't too confusing. What I want to do now, though, is I want to tell you, well, holography is useful for something that you may not have thought of beyond quantum gravity. And that is, it's actually useful for studying strongly interacting systems in the real world, more down-to-earth physics than quantum gravity. So I'll move on. Okay, I want to describe strongly interacting systems and what they are and why you should care, and then I'll relate them, I'll tell you what they have to do with holography and string theory. But to describe strongly interacting systems, I'm going to start with the simplest system you can imagine. So forget about quantum gravity and string theory and all that fancy stuff. Let's just start with the simplest thing of particles in a box. Okay, so we have a box, and there's some particles floating around inside, and they're all moving with some momentum. So I'm going to build up to strongly interacting systems, but I'm going to start with the simplest thing of a non-interacting system. And as that name suggests, that means the particles in the box don't interact at all. So what that means is that if two of them approach each other, well, nothing will happen. They won't interact, so they'll each just pass through the other one. Each one will just keep going the way it was, as if the other one isn't there. And the point I want to get across is that this system, at least as a theoretical physicist, this system is under control. So we can write down the equations describing the motion of the particles, and we can solve them. And so we can calculate pretty much anything you want. We can tell you where each particle will be, given the initial conditions. We can tell you where the particle will be at any later time. We could tell you, the temperature in the box. We could tell you the pressure on the walls of the box, and so on. So this is considered a solved problem, but of course it doesn't really describe the real world, because in the real world, particles interact with each other. So the next level of complication, the next level of difficulty is a weakly interacting system. And so what happens in this case is as the particles approach each other, well, if they interact weakly, they'll each just give the other a very weak kick, or a very weak push. And so each one will experience a slight deflection, as I've tried to indicate in the picture. So it doesn't keep going exactly the way it was. It might change direction or momentum a little bit, subject to conservation of momentum. So this case is mostly under control. We can write down the equations. We can't always solve them exactly. I mean, in some special cases, we can solve them exactly. But generically speaking, we can't solve them exactly, but we have very good approximation techniques, namely perturbation theory. But we have very good approximation techniques where if you just work hard enough, you can get a better and better approximation to the answer, and you can predict the motion of the particles. And so you can calculate almost anything you want. I won't say everything, but you can calculate most anything you want, at least to some accuracy, in some approximation scheme. So in any case, this is considered a mostly solved problem in physics. There are some open questions, but it's mostly solved. But of course, that brings us to what I really want to talk about, which is strongly interacting systems. So in this case, when the particles approach each other, each one gives the other a very big kick. And so they can radically change trajectory, as I've tried to indicate. And you can get very complicated motion that's very difficult to predict. In this case, again, broadly speaking, is not under control. There are special cases, in general, we can usually write down the equations that describe a strongly interacting system like this, but we usually can't solve them. There are special cases where we can, for example, systems with special symmetries, but in general, it's considered a major open problem of how to calculate anything in a strongly interacting system. And in fact, there are even cases where we don't know what equations to write down. But even if you do know the equations to write down, they're practically impossible to solve using any existing techniques. And it's not just a theoretical problem. It's a problem that's important for the real world because there are materials, real materials, in which the electrons are strongly interacting. And these materials have remarkable properties that could produce revolutionary devices. And I've given a few examples here. So one example is high temperature superconductors, which could dramatically improve energy efficiency, for example, in power cables. Another example is topological insulators, which could be the basis for quantum computing. And another example is graphene, which, as the picture there indicates, is a sheet of carbon atoms arranged in a honeycomb lattice, which has remarkable properties. I mean, it's very flexible, it's a very good conductor, and so on. And it could be the basis for a new generation of electronics. And in the lower right is a picture of something you could potentially build with graphene. This has not actually been built, it's just an idea. But using graphene, you could potentially make something that's like an iPad, only it's as thin and flexible as a sheet of paper and also transparent. Not entirely sure why you would want that, but in principle, it's possible. But anyway, my point is, these are all cases with the electrons in these materials are strongly interacting, and they have remarkable properties. For example, their conductivity, or things like that. And in most cases, we know what equations to write down, but because they're strongly interacting, we don't know how to solve the equations. So we don't have good theoretical or mathematical control over these systems. And so experimentalists keep collecting more and more data, but the theorists are at a loss because of the strong interactions. So what does any of this have to do with holography and string theory? So here I'll try to tie everything together. So let's go back to holography. So here are my strings moving around on a space with the boundary, and then living at the boundary are my quantum mechanical particles with no gravity, which are the hologram of the string theory. What I didn't tell you before was that when those particles are strongly interacting in the sense that I described, the strings are actually weakly interacting. And this is really good news, because what this means is that although I can't solve my equations for the particles when they're strongly interacting, if I can translate to the string theory, well, the strings are weakly interacting. And so on that side, I can solve the problem, and I can do some calculation and then translate back to get an answer. And so in fact, and this is I think this is my last slide, this is how my research works. So I look at these systems in the real world that I mentioned before, high temperature superconductors, topological insulators, graphene, and others. And I look for questions that people don't know how to answer. That theoretical physicists don't know how to answer because of the strong coupling. They don't know how to solve the equations. I go to holography and I formulate those questions about my particles. I then translate to the gravity side, or the string theory side, where I do know how to solve the problem. So I do some calculation there, and then I translate back to get an answer about the strongly interacting quantum mechanical particles. And so in that way, you are able to learn something about strongly interacting systems, and hopefully learn about all the behaviors listed here and lots of other things. I should say that in general, the systems that you study in holography are not exactly the ones that describe the real world, so they're not exactly the ones in, say, a high temperature superconductor and so on. But you are hoping to learn general things about strongly interacting systems. Some kind of general principles about how these systems behave, why they have unusual properties, and so on, that you can't solve any other way. In a lot of cases, holography is the only way we have, right now at least, the only way we have to solve the equations. And with that, I think I'm more or less done. That was my summary of strongly interacting systems, what they are and what they have to do with holography and string theory. So I'll just end by going back to the beginning. So my research, summarized in a single sentence, I use a tool from string theory called holography to study strongly interacting systems. And hopefully now you at least have some idea of what each of these is and why you should care. But the real punchline, the takeaway message that I want you to remember is that if you ask what is string theory good for, well, one answer is that it is the leading candidate for quantum gravity that describes our universe. However, I hope I've convinced you that there is another answer, that because of holography, string theory is also a useful tool for studying strongly interacting systems. And I want to emphasize that because I think people don't hear it very much. Most of the time when you hear about string theory, for example, in the press or from other physicists, usually you hear the first answer. You just hear about quantum gravity and you don't hear so much about the second answer. Even though nowadays, I think most string theorists are actually working on the second answer. They're working on holography and strongly interacting systems. And finally, if you want to know more about all of these things, I can recommend a few books. One is The Elegant Universe from Brian Greene. It's about 20 years old now. There's a more recent book called Why String Theory from Joseph Conlon. It's a little more up to date. It has a little bit more about holography. And of course, that's my email address, so you can email me and ask questions. And I believe I think you've been submitting questions during the talk, and I think now we're going to have some Q&A. So I'm happy to answer questions now. But anyway, with that, I'm done, so thank you for listening.
Thank you, sir, for your wonderful presentation, sir. So I have a guest with us from USA, Richard Marker, and we have got some question in comments. So if we allow, we can start our discussion to some. So Richard Marker,
yes.
can you hear? Yeah. So thanks for joining with us. So if you have a question to our speakers, so you can ask.
Thank you for your presentation. I enjoyed that. That was very good. The question I have, I don't know if there's an answer to it, but if you're using holography to represent the universe, say, for example, and does it need to be a bounded surface, or can it be like a flat surface, and that the holography can project a third dimension? And if so, if the flat surface has a granularity, how much granularity can the third dimension have?
So the answer to the first question is yes, it can be a flat surface. It doesn't have to be bounded. There are examples where it's not bounded. So that part is relatively easy. And you can essentially take, if you have some theory of quantum gravity in some space, for example, you can cut it in half with like a plane, which is not bounded. And then what's supposed to happen is, basically each side, there's a hologram living on that surface. Now your second question is actually much more difficult. And indeed, the answer is not known. I tried to suggest, I can go back to this picture, my cartoon picture that I had, something like this. And the question you're asking is, well, if you have some granularity, say, at the boundary, how does that translate into some granularity in the bulk? That part of this mapping, or the dictionary between the two, is actually poorly understood. We don't have a precise or exact mapping that if, for example, if you have a lattice at the boundary and there's some lattice spacing,
Okay.
We don't know exactly how that maps to how that maps to some kind of lattice spacing in the bulk. We don't have many examples of it. And in fact, in general, it is part of a more general and more difficult problem of just how does that extra dimension emerge. The current state of the art is we really just have lots of examples of this. And we sort of study those examples, but if somebody just hands you, a quantum mechanical system and asks, what is the holographic tool, in the extra dimension, we don't know how to derive it. So yeah, unfortunately, I don't have very much to say about
thank you. That helps, actually. It gives me an idea of what is possible.
Yeah.
The nemesis for the source of my question comes from, I've been able to look at a flat kind of structure for the universe, but I have difficulty getting it into 3 dimensions, but there's considerable phase information included in the structure itself, the flat structure. It sounds like the phases are capable of going into a 3rd dimension, so conceivably the universe could be a hologram, it seems, but I don't know that.
So, okay, you're saying our universe is a hologram of some higher dimensional, like there's an extra dimension.
actually a lower dimensional flat surface that has higher dimensions in the form of considerable phase information interaction.
Yes, that's that's possible. I've heard of things like that.
Thank you. I appreciate the
Yeah.
consideration of the
Yeah.
question.
Thank
There's a-
you,
there's a-
Richard, for joining with us. So we have
Yeah.
some question in our comments, so we can go to our question. So the first question: what is the state of an electron, and what does an atom really looks like?
I'll answer the second question first. I'm not super expert in this, but there are people who do imaging of atoms using scanning tunneling microscopes and things like that. And the images they get, at least the ones that I've seen, are actually somewhat similar to the image of the hydrogen atom that I showed. When you get down to those scales, sorry, I'm flipping through my slides really quickly here. Here's my hydrogen atom. Here it is. As I mentioned, this is a result of a calculation that we ask our undergraduates to do, just solving for the ground state of the. This is actually the probability density for the ground state of the hydrogen atom. When they image them, for example, if you take a metal, a piece of metal or something, and you do some scanning tunneling microscopy of the surface, you see the atoms, but they're not. They don't look like this picture. I mean, this is some cartoon picture. Instead, they usually do look just like these fuzzy lumps that are arranged in whatever crystal structure you have in your metal or whatever it is. And also, you can see pictures of on the surface of a metal, for example, people will put an atom, and what you'll actually see is either a lump or some kind of spike, because what they can actually measure are things like with a scanning, for example, with a scanning tunneling microscope, the probability for the electrons to tunnel through to the atom. So you get the image you get is actually some probability distribution. But the point is, it's fuzzy, right? It's not, because of the uncertainty principle, you're not going to see like the atom at one particular location. You're going to see a dense cloud somewhere. And for the first part of the question, what is the state of an electron? I didn't quite, I mean, it depends on the circumstances. I don't know if, I mean,
Okay, sir.
yeah.
So
I don't know
thank
exactly
you,
what they
sir.
had in mind for the first question.
Okay, so thank you. So we can go to our next question. So is uncertainty property of the system, or it's the property of our observation?
Oh boy, yeah, I think I might pass on this question. This is, yeah, I'm going to take the pragmatist point of view and just say it's just a fact of the experiments. It does get into sort of the theory of measurement and even into philosophy of quantum mechanics that I'm definitely not qualified to comment on. Most physicists, in my experience, they think about those questions a little bit and then they move on, and just the sort of shut up and calculate approach of the equations work. And yeah, I don't have any informed opinion about that, so sorry.
Thank you. We have another question. So what is the difference between black hole singularity and cosmic singularity? If the entire universe itself falls down its own black hole, cosmic singularity develops.
Yeah, they're both singular. Let me go to my picture. The cosmic singularity, I think, in some sense is worse because it's much, the curvature that I was, the warping of space and time is much bigger. And so it's a harder problem. There are ways actually to quantify that statement. So you can characterize these singularities mathematically by their topology. There's theorems about how bad the singularities are. It doesn't really help. That helps with some questions, but it doesn't really help with quantum gravity. What else should I say? In general, Yeah, I'll just say in general, the cosmic singularity or the Big Bang singularity, it's a harder problem actually than black holes, because it's all the matter in the universe. There's not, and in particular, I mean, with a black hole, there's a chance you can observe them, like in this picture. They don't emit anything, but stuff around them does, and you can also see them interact with other objects. The cosmic singularity is a different animal because all we have is the observation we see in the sky today, and what we can learn about the history of the universe from that. And it's very difficult to see, before the CMB, basically, which was 300,000 years after the Big Bang. So we can't actually observe it really. And furthermore, there's only one. We believe there's lots of black holes out, for example, at the centers of galaxies, a lot of galaxies. But there's only one Big Bang singularity. So you can't do statistics, you can't do experiments. There's just the one, and we can't really see it. So mathematically, it's a more difficult problem. It's actually a worse singularity with much worse curvature. And then also just practically, it's a harder problem. Does that answer the question? I hope that does.
Thank you, sir. This may be the last question. So what is the physical significance of Planck's mass?
Sorry?
What is the physical significance of Planck's mass?
Okay. The short statement is the Planck scale, the Planck mass. There's a Planck scale, so gravity, Einstein's theory of gravity, actually has a built-in scale. It's given by Newton's constant. You can take Newton's constant and combine it with, I think it's h bar and the speed of light c, and some other things, and get well, you can express it either as a length scale or as a mass scale. That's the Planck length or the Planck mass. And the significance of that scale is that it's precisely the scale where gravity, well, basically where quantum gravity becomes important. It's where Einstein's theory effectively breaks down. When the curvatures reach that scale, you no longer trust the theory. And you need, like I was saying, well, I'll put it this way, you need some other degrees of freedom. That theory by itself can't describe what happens at those scales. I wish I could remember the number. Oh, well, it's close. If you express it as a length scale, it's actually kind of close to the 10 to the minus 33 centimeters. I think it's actually larger than that. I want to say 10 to the minus 31 centimeters. I should remember what the Planck length is, but it's somewhere, it's very small, and it's the scale where Einstein's theory breaks down and you no longer trust it. And you need a quantum theory of gravity with some additional degrees of freedom. And by the way, in string theory, though, you have no problem in principle, at least studying physics at the Planck scale. And the way string theory, well, I won't go into too much detail. I mean, string theory, you do get some new degrees of freedom, which are excitations of the string, which can do things. They can do things like remove the singularity. So in GR, or in Einstein's theory, it looks like you're getting a singularity where the space and time become infinitely warped. But in the string theory, you actually find, well, the warping isn't infinite because the strings, excited strings are there, and they can actually cut off the curvature. Anyway, I'm getting technical. I hope that answered the question.
Thank you, sir, for your wonderful presentation and nice discussion, sir. So I think students have learned a lot of things about the string theory and the holography. So thanks for giving me this opportunity to arrange an important webinar with you, sir. So it's a great webinar with you, sir, and students have learned a lot of things. So thanks again for joining with us, and thanks for giving me this opportunity. And we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation, sir. And thanks, Richard Marker, for joining with us. So thanks again, Dr. Andy, sir, for joining with us. So we, in the near future, I will arrange another webinar with you, sir. So we have organized this webinar in this corona pandemic situation to motivate and encourage our students. So I have successfully completed our 107 today. So thanks for giving me these opportunities, and hopefully some of us today they motivated, and hopefully in near future they may do their research in fundamental physics, and hopefully they do some finding in high energy physics and in their related physics. So thanks again, and bye for today.